Welcome to our first lecture, Our Place in Space. I like to start off with this particular slide and these images because it does give us a very interesting and unique look at kind of our perspective on history and our perspective on astronomy over time. The large picture on the left is the Hubble Ultra Deep Field picture. So this is what Hubble telescope saw when it was pointed to an apparently very, very blank place in space from our point of view here on Earth. And in this picture, there are just a couple of stars. So these things with 4 points, and those points are just an aspect of the telescope itself. And then there's one more up here at the top. So I see 4 stars, including the one at the bottom, but everything else in that picture is a galaxy. And so for most of you, this is kind of your normal. This is what you think of when you think of astronomy, as these beautiful Hubble and other space exploration type pictures. But what we have over here in the upper right hand side are some of the pictures from the very first telescope used for astronomy. So Galileo took the telescopic instruments that were being created by the Dutch and the Danes at the time, Hans Lippershey and other patent bearers, and turned them towards the heavens. And so these are some of his first sketches of Saturn as seen through his little telescope. And his little telescope was no better than common binoculars that you have today. And then another really interesting piece, an artifact of our view of space, is the very first astronomical image taken, the very first astronomical photograph, so to speak, on metal. And this is of the moon, so taken through a telescope. So I just wanted to share these as our kind of a history of our views of astronomy over time. So our objectives as we start getting into this course, this very first unit is fairly large, but it does give us an anchoring for where our place is in space. Talk about size, talk about distance, talk about light, a little bit of history, and we will come back and touch on these points as we go through the course. So where is our actual place in our universe? So the universe is large and it's vast, and we are riding along on our planet Earth. And so in this image you can see the planet Earth, and then as the image zooms back in, it's taking you to, there's the Earth, and then there's our place in the orbit around a particular star, and then that star in that solar system with all of the planets around it is in a particular spot on the arm of the Milky Way galaxy. The Milky Way galaxy is one of several in a local group, and the local group happens to be in a supercluster of stars. So this little image is just to kind of show you that we can keep zooming ourselves backwards and see, this larger unit that we belong to. Another way to think about that is if you had to address an envelope to yourself. So pretend that there is a universe intergalactic lottery, and you're the winner, but they need to know how to address the envelope to you. And so this is coming from, far, far, far across the other side of the universe. So how would you address the envelope to yourself? So you might start off with your name. You might start off with your street address and the city and the state and the zip code that you're in. And so that would normally work for our postal carriers, but we're talking about intergalactic postal carriers. So how would they know where to find you? So stop and think about that for a minute and maybe jot down some ideas. Go ahead and hit the pause button, jot that down, and then we'll come back. All right, so hopefully you did pause and actually thought about it. So if you were going to do that and take yourself further back, we're going to have some words that we might need to help clarify so that we can all use the same terminology. So let's take a look at some quick definitions, and then we'll take a look at what that address might look like. So a star. So our sun is a star. The next closest star is Alpha and Proxima Centauri. It's a double star system. They're rotating around each other. But these are large balls of gas, and they have so much stuff in them. There's so much mass that the pressure in the center causes it to be hot enough for fusion to happen. So stars, large balls of gas. Planets, like the Earth that we ride on, tend to be moderately sized objects, and they tend to orbit stars. They don't shine on their own. They just reflect the light from their host star. Moons and satellites are things that orbit planets, and they also just reflect the light of the sun. So getting smaller, asteroids and comets often get confused. Asteroids are little relatively small rocky bodies that orbit a star. Sometimes they get trapped in orbits and caught by other planets temporarily. They get knocked about, they get slingshotted throughout the solar system, but in general, orbit their host star. Comets are also relatively small, but they tend to be icier for a period of time. So they form far enough away from the sun that they keep kind of all of the ices that they have from the beginning of the solar system itself. They do orbit a star. Some of them come in and orbit that star on a fairly regular basis of, between a couple of years to 100 years, and some of them are up to thousands or more years. So comets, dirty snowballs in space. Asteroids, little small rocks in space. Rock potatoes. So a star system, our solar system is a star system. We have a star, just one, and it's all of those materials that happen to go around it. A galaxy is a much, much larger component, and oftentimes you'll hear people take the words universe, galaxy, and star system and actually use them interchangeably, but they're not. So a galaxy holds all of those other solar systems and gas and dust, and sometimes even smaller little satellite galaxies kind of all orbiting its large central mass. So a huge island of stars. Nebula. So nebulas are big clouds of very, very fine dust and gas, and oftentimes nebulas like the one that you see in front of you, which is in Orion, and so it's got two distinct little nebulas, but that gas and dust is where stars are born, and that's what stars need. So this is a little picture of a stellar nursery there in Orion. So nebulas. So the universe is really going to be the sum of everything. And I have a Douglas Adams quote here because I really like Douglas Adams, and Hitchhiker's Guide's got some great quotes in it. But space is big, really, really big. You won't believe how vastly, hugely, mind-bogglingly big it is. And I kind of feel that this is absolutely true. So our cosmic address, right? So go back to that envelope, and if you were going to address it. So we've got the whole address down, and then you might even just need to point out that if you're speaking, like for example, I live in the Puget Sound area, so then I might just say that I am in the Northern Hemisphere, I'm in North America, I might even give a latitude or a longitude, and then I'm on the planet Earth. And I orbit a star we call Sol, and we happen to be the third rock, right? We're the third planet in that orbit, and that I am in that solar system, and that solar system happens to be in this particular interstellar neighborhood, so other stars that are very close by. And what that neighborhood looks like, I happen to sit on a spur of an arm on the Milky Way galaxy, and there's a little red line to show you just about where that is. The Milky Way galaxy is part of a local group. The three largest galaxies in there are the Milky Way, Andromeda, and Triangulum galaxy, and that local galactic group with all of its other little satellite galaxies is part of the Virgo supercluster of galaxies. And each one of those points that you see in this image are all galaxies, not stars. So the Virgo supercluster is part of another supercluster, and then all of those clusters, all of those little islands of massive amounts of galaxies kind of make up our observable universe. That's a pretty long address to have. So when we have vast distances like that, and we have to, move things or look at things and communicate over vast distances, our form of communication in astronomy is light. We can't reach out and touch a star. I mean, we are made of the stuff of stars, so everything around us is made because stars in the past have reached the end of their life, and in many cases they were massive enough and would explode in space and then repopulate all of the nebula out there with heavier materials, and that goes on and on. We've kind of got a cosmic recycling. But light is really the way we work in astronomy. It's how we understand things. It's how we know things. It's how we can tell if a planet's going around another star someplace far, far away. So understanding light is important. We'll spend time on that as well. But light is going to tell us a lot about distance, and it also tells us about time, because light travels at a set speed, and that becomes very, very helpful. So when we look at the moon, the light coming off of the moon that's being reflected from the sun takes 1 second to get to us, right? Light from our sun takes 8 minutes to get to us. From Sirius, the bright star, and Canis Major, the big dog, one of Orion's hunting dogs, it takes 8 years for that to get to us. And from the Andromeda Galaxy, you're looking at 2.5 million years. So they're kind of like little look-back clocks. For example, the sun. If the sun, on a beautiful, bright, sunny day, if you're looking at the sun and for some reason the sun just turned off, no light, you would not know it for 8 minutes. All that light that was there would still be traveling towards you, but you would not know that for 8 minutes. Again, we're looking back at our Orion Nebula here, and so that Orion Nebula is 1,500 light years away, right? So anything that happens in that nebula, that distance in time, it would take 1,500 years before we actually saw that change happen. Likewise, if we see a change, we have to calculate backwards in time when it happened. So one way to think about that is to find a birthday star. So there are stars out there, and you can look them up in the back of your book. Find one that is about, so if my 4.5 birthday was coming up, right? I was going to be 4.5 years old. Then I could take a look and I would realize that the light that left Proxima Centauri the day I was born would reach me on my 4.5 birthday. That's what I mean by birthday star. So, light traveling can tell us not only information about the object, but how far away it is. So here's a little look back time generator. I'm going to pop over so we can take a look at it together. So there's that 1,500 light years in the Orion Nebula, and here's our little observer. So he can see it. He can see that star. So we're going to say there's a beautiful star in that nebula, and it's going to go supernova. So it's going basically at the end of its life, can't hang on to it, cannot process any more material in the core of the star, and it's going to go through its death throes and go through supernova. So its supernova's out. There it goes. And here's the length of time that it takes before our little observer here gets to see it. So then the further away that observer is from the actual object, the longer it is going to take for us to realize that the object is now extinct. Poof. Okay. So here's a real life picture of this. So this was a supernova that happened not too long ago, and it was actually something that we could see. They're incredibly bright, hugely energetic episodes in astronomy, and this happens to be in the Whirlpool Galaxy. It's right off the handle of Ursa Major. The asterism you know well in that constellation is the Big Dipper. And you can see on the left, and this is in 2010, there's a segment right here at about 7 o'clock on the spiral arm of this galaxy, and it's just what we'd been seeing for time, and then all of a sudden a brand new quote-unquote star appears. And so if you compare the brightness of this star to the core of that galaxy, all of these other points of light, these are not stars in that galaxy right here, the Whirlpool Galaxy. These are foreground stars. These are in the Milky Way Galaxy, but that one is. So big, big event. We know about when it took place because we know approximately how far away that galaxy is. All right. So now another interesting point about that is when we take a look at something like the Andromeda Galaxy here, So 2.5 million light years away. But the other thing too is that when we see this image, we have to remember this galaxy is about 100,000 light years across. So that means that the light that we see in this image is different in age on the back side of the image as it is on the front side of the image. All right, so that's a lot to keep in mind. So we've talked a little bit about a light year in the observable universe. Okay, so what is a light year? So we talked about having a constant rate. It can get around the Earth about 7.5 times in a second, and that rate is 300,000 kilometers per second. So that's how far it is moving. And so by measuring stuff back in light years, it becomes a much easier number for us to handle because there's smaller numbers. But if we wanted to change that to kilometers, from light years, you're looking at roughly 10 trillion kilometers. And there's an example of the math in there if you want to kind of cross-check that. It's rounded up. Rounded up to 10 trillion is just fine. We don't have to have... Okay, so we talked about light speed and light years, and so that's one unit of measure. But when we get closer into our own solar system, sometimes in the inner planets especially, we can use astronomical units. In an astronomical unit, we just took the distance from the mean distance from the Earth to the Sun, and which we will call 1 astronomical unit. And so we can measure within our solar system that way, and that works out pretty well. We can also use light minutes and light seconds. But for example, Voyager 1 is about 127.7 astronomical units from Earth, and this was as of the last time I looked this up, which was in 2015. So if you can imagine, this spacecraft has gone 127.7 times the distance between the Earth and the Sun. Okay. Okay, so as far as how far back we can see, this is changing constantly over time, right? So we went from just naked eye to then Galileo's little telescope to be able to see what was going on within our own solar system. And then we keep increasing our telescopic powers. I mean, in some cases, things like the Andromeda Galaxy we thought was part of our own galaxy. We thought it was just a smudge, a nebula up there. But as we have been able to better understand light and better understand different objects in astronomy, we're able to actually understand those distances better and better and better. So really what we have is the observable universe, and that is how far back we can see. Alright, so what did we do in the first part of this lecture? We basically took a really quick look at our place in our own solar system and our place in space, and then how things unfold into the universe. You can kind of think about that as our galactic address. Talked a little bit about the further away things are, the longer it takes the light to get to us. So the light we see is what that object looked like when it was a little bit younger. And that those distances, because light travels at a set rate, that we can use light to help us measure distance, and it's all tied together. Alright, so we're going to wrap up the first part of this lecture. There's some activities that you will be doing, and then you'll come back to the second half of the lecture.